This video presents the contents of the paper Self-Supervised Learning of Adversarial Example Towards Good Generalization for Deepfake Detection. Authors are from the University of Adelaide and Tencent AI Lab. The aim of generalizable deepfake detection is to enable a detector to generalize to forgeries created by unknown methods. Assuming the training set consists of forgeries created by DF and FGF methods, a good deepfake detector is supposed to classify a given image as real or fake regardless of its creating method. Note that when the test and training forgeries share the same creating method, a simple exception model can achieve an accuracy of about 98. So the real challenge is when the deepfake methods are unseen during the training. The deepfake detection problem has drawn increasing attention recently. We can categorize these arts into three types despite the varying details. The first results to a more complicated network structure. The second is augmentation. We know creating forgeries is easy because we can just swap the pixels in the background and foreground to obtain a new face. The last type tries to explore low-level clues. This is also the most popular direction recently. The clues including boundary artifacts as seen in the right line in the left image. Frequency artifacts, which are more obvious than that in the RGB space. Detailed discrepancy that indicates an image consists regions from different sources. As shown in the right figure, the center part in the image is different from others. For all the low-level based methods, we know there are high risk of failure for a simple post-processing step, such as compression, which can easily destroy the clues. Our method is developed by one guiding principle. A generalizable representation should be sensitive to various types of forgeries. To push the principle to the limit, we propose two specific steps. First, we propose to enrich the diversity of forgeries by augmenting forgery images from a large pool of configurations, which are the multiple choices of blending region, type, and ratio. Second, we propose to enhance the sensitivity to forgeries by predicting forgery configurations in addition to judging if it's a forgery or not. To seamlessly integrate the two steps, we propose a unified adversarial framework. Specifically, during training, we randomly select a reference image if the input is real. These two images are sent to a synthesizer network to select configurations that specify the facial forgery region, the blending type, and the mix-up blending ratio. Then a new forgery is produced based on these two images and the selected configurations. After synthesizing, the forgery is passed to our detector for the real or fake and configuration predictions. For the synthesizing step, there are three blending methods including alpha, Poisson, and mix-up blendings. The formulation for the mix-up blending is given here. We use implementations from the CV2 package for the other two. Examples for all the methods are given in the figure. As for the blending mask, we have a total of 10 choices for the mask region selection. Left eye, right eye, nose, mouth, and their different combinations. For the losses, we have the main task loss L-main, forgery region estimation loss LR, blending type estimation loss LT, and blending ratio estimation loss LA. The tau in LA is binary and is set to be 0 only if the mix-up blending type is selected. For the adversarial framework, assuming W is the parameter for the detector and theta for the synthesizer, we aim to minimize the overall loss regarding W and maximize it regarding theta. Please refer to our paper for details. We conduct experiments by generalizing to different datasets and different compression levels. As listed in the tables, our method achieves favorable performances against existing arts. This indicates that our method is more robust than others, despite the varying creating methods and post-processing steps. We also present TSNE visualizations for the baseline and our method. As shown, both the two models can well separate real and fake images, but the baseline model reveals unique artifacts of each face manipulation algorithm, as the dots from different methods scatter clearly. By contrast, the dots are mixed together in ours, indicating that our method can find more common features among the forgeries for better generalization. Thanks for watching. Link to the codes is in the paper. Please contact me via email if you have further questions.